Okay, so let's think of the hydrogen atom where the potential is spherically symmetric, minus z e squared over the radial distance. I guess this is in CGS units. Hydrogen has z equals to 1. And so the Schrodinger equation now looks like second derivative of u in R minus, well, if z is 1, it's minus e squared over R times u equals EU. This is now hydrogen. And so this, as R goes to 0, this goes to minus infinity. So we have this singular point at R equals 0, but there's some physics there that changes things, right? There's the nucleus, so really we want something like, as we approach R equals 0, we really want a potential that goes to positive infinity. So it's more something like that. So we have the conditions that at R equals 0, u is, well, that's 0 because R equals 0, and u of R equals infinity it's also equal to 0. So this comes from not allowing, well, u is R times the wave function, so R equals 0. As long as the wave function doesn't go to infinity there, and that's not a possibility, right? That's finite, so u has to be 0 there. Let's construct the solution u from this. So let's say that at large values of R, we'll explore it in that regime first. So that means that this thing is negligible, right? That goes to 0, and so the Schrodinger equation looks like that this is about equal to the energy times the u function. And if we're thinking of, well, all states are bound, so E is actually a negative quantity. And so we know what the solution of this kind of equation is. It's like the solutions to the particle in the classically forbidden region outside a finite square well. And so the solutions have to be of the form well, proportional to e to the minus some coefficient times r, where b is some positive constant. And so let's see, what condition do we get on this? We take derivatives of u and r, and that goes like, we have minus b e to the minus br, and second derivative goes like b squared e to the minus br. And so the Schrodinger equation tells us that minus h bar squared over 2m, second derivative, which is b squared e to the minus br, that's equal to the value of the energy times e to the minus br. And so we conclude from this that the energy is equal to minus h bar squared times this coefficient squared over twice the mass. And so b squared, of course, is a positive quantity. It's related to E by this equation. So we can say that the u function goes like e to the minus square root of minus 2me over h bar squared times r. So this is for large r, the solution has to look like that. But we also know that u of 0 has to be 0, right? This condition here. And so this tells us that if we want a solution that's valid everywhere, our function, our lowest energy function, which has 0 nodes, so we'll make it go to 0 only at one place, which is at r equals 0. This has to look like r times this, r e to the minus br, or r times this, right? So that's what our function looks like. So let's substitute this. Well, really should write r e to the minus square root of minus 2me1, where e1 is this lowest value of energy, times r. And that thing, if we put it into the Schrodinger equation, we should get a constraint on the energy. So let's see what this looks like. So we have minus h bar squared over 2m. We have to take a derivative in r of a derivative already. So that's minus br e to the minus br plus e to the minus br. That's the first derivative. Then we have minus e squared over r e to the minus br, that's equal to e1 r e to the minus br, minus h bar squared over 2m, we get minus b e to the minus br, plus b squared r e to the minus br, minus b e to the minus br, minus e squared e to the minus br is equal to the ground state energy, r e to the minus br. So we get minus, let's see, minus h bar squared over 2m, minus 2b. We combine these, plus b squared times r, minus e squared is equal to e1 times r, right? So we got rid of the e to the minus br. B squared, so b squared is equal to minus 2m e1 over h bar squared, right? We have to write this. This is an equation for e1, so we can find the value of e1. We get minus h bar squared over 2m minus 2m e1 over h bar squared minus 2m e1 r over h bar squared minus e squared equals e1r. What do we get here? We get h bar squared over m square root of minus 2m e1 over h bar squared minus e squared equals 0, and minus 2m E1 over h bar squared equals E squared m over h bar squared squared. And therefore, this lowest energy is equal to minus m e to the fourth over 2 h bar squared. We can write this as just in terms of h. So we have a 2 pi which we square. Here we have a 2 here, so we get a 2 pi squared m e to the fourth over h squared. And this is the value of the ground state of the hydrogen energy that Bohr was able to get thinking classically.